Hello, this is Team 23, Wireless Inductive Charging Unit, WICU. My name is George Perez.
My name is Alejandro Esteves.
My name is Gabriel Alvarez.
My name is Jose Rodriguez.
My name is Alex Casas.
My name is Jose Endia.
Hey dude, can I please charge my laptop? It's dying already, man.
No, please, let me charge my phone.
But there's no more outlets left.
Hey guys, have you heard about wireless charging?
What?
What?
Hello everyone, we're here to present you WICU, Wireless Inductive Charging Unit. Here is my partner Jose, he's going to work with me. We have the oscilloscope, we have our power amplifier, we have our power supply, we have our frequency generator that we're going to be using in this project. We have our first coil, second coil, and my partner here is going to turn on the power supply so you can see on the oscilloscope the voltage that we picked up on the secondary coil. As you can see, if we keep the coils, we increase the distance between the coils, the voltage is going to decrease. And if we get them closer together, the voltage is going to increase. And at the same time, you can see the effects of the LED. We're not turning off the lights, so you can see it better. You see the LED, the brightness diminishes as you increase the distance, and the brightness increases as you get them closer together. Thank you. With the frequency that we're using in this setup is 32.4 kilohertz. How did we come up to that frequency? Well, we use the formula 1 over 2 pi, the square root of LC, L being our inductor, the first coil, the secondary coil, and the C being our capacitor of the resonant circuit. We've calculated the inductor by using the oscilloscope, and that turned out to be 0.13 millihenries. We use a capacitor of 0.22 microfarad that you can see is right here on each side of the coils. That gives us a frequency of 29.8. As you can see, this frequency is a little different than the experimental value that we found out, and that's mainly because we use some elements that have some tolerance of like 10%. For example, the capacitor. Plus the inductors they will use a rough estimate to find out the inductance. The efficiency is dependent of the Q1, Q2, and K, being the Q1 the quality factor of the first coil, the Q2 being the quality factor of the second coil, and K being the coupling factor. The Q1 and the Q2, they are dependent on the geometry of the coils, the distance, the radius, the thickness of the wire, and the K is dependent also, it depends on the distance of the two coils. As you increase the distance, the K decreases. As you get them closer together, the K increases. The K can range anywhere from 0 to 1, and our system is between 0.1 and 0.2. We're using our setup, we're using on the primary a series resonance circuit, as you can see, because the coil is in series with the capacitor. In the secondary coil, we're using a parallel resonance circuit because the capacitor and the inductor they are in parallel. Also, we want to show you the effects of having the coils in perpendicular to each other. Once you got it in perpendicular to each other, the flux of the first one is not going to be able to generate power on the secondary coil because they're on a different plane. So you can see the LED. The LED loses power, and once you line them up, once you line them up, it increases the brightness. Thank you. Well, that's what we have for our project, and we're gonna be using this for our Senior Design 2 project to charge an electric vehicle. That's gonna be the primary. We're gonna set up that in a garage, or it can be in any other environment, and the secondary is gonna be attached to the vehicle to charge the batteries of the electric vehicle. Thank you very much.